So today we are starting the Monte Carlo integration because we're going to simulate the random observation from MCMC method, which is Markov and Monte Carlo technique. Okay, so that's why we require the basic of first of course Monte Carlo. So we have studied so far the basic of inverse transformation method using the acceptance suggestion method. Okay, so there's another technique, Monte Carlo integration technique, which is helpful in MCMC. Okay, so that's why we require here Monte Carlo integration. Okay. So this is all basic about that optimization technique, and integration problem is mainly the two major problem. Okay, under this category. Now just look at this particular expression. This particular expression, that is your integration. Here, if you just observe this particular integration, that is integration from h of x to f of x. If you just consider this is some function, maybe x square or maybe x raised to 5 or some function of x, and this is the particular density functions. Okay, so normally one can get using the you can very easy to get the integration using integration function in RStudio, and you can get the values of this directly in the RStudio. That's not a problem. But suppose you want to do the simulation from this particular PDF, which is your target PDF, and but this particular target PDF is difficult. Okay, so you cannot generate the observation. This is your this f of x is your density function. Okay, which may be binomial, which may be the normal, but this particular function h of x is a complicated. Okay, this particular function h of x is constant. So this is something like your expected value of your x, which is same as maybe integration x into f of x d of x. So if you just consider this x will be the function of h of x, then one can use the concepts of the Monte Carlo techniques. Okay, but when do you going to when are you going to use these functions? When this particular function h of x is a complicated functions. Okay, so how basically this particular things works. So suppose you want to compute the integration of let's consider this example. This example, suppose you want to do the integration of this particular function, which is integration 0 to infinity x raised to lambda minus 1 exponential of minus x. Okay, see, normally you can in RStudio you can integrate, you can use integration function and you can get these values, right? It's something but your gamma lambda. Okay, using this maybe the gamma functions, you may get the answer immediately. You can get the answers. Okay, but you want to generate the observation. You want to generate the observation from this function. Okay, but look at this function is a complicated function. So you can generate the observation from f of x. You can generate the observation from f of x. Maybe you may say 1,000 times, and then using this particular function, you can obtain the mean of this function. So this particular integration will be approximated to 1 upon n summation of h of x. H of x, where I is running for 1 to 1. So what exactly I am doing here? I am generating the observation from this particular function. Okay, and taking, there are the total, suppose 1,000 observations. So you are just finding the mean of this particular h of x function. So this particular integration is exactly same as this particular value. So we can just look at using this maybe the RStudio, how this value will be approximated to this particular values. Okay, so when are you going to use this function? whenever h of, see, this is your PDF, correct? This particular f of x is your PDF, but the h of function is complicated function. Okay, so you generate the observation from this f of x, and considering the bicentral limit theorem, one can say that this particular integration will be approximated to average values of a function of h of x. So this answer and this answer approximate will give you the same answers. Okay, there are a lot of theory parties there. You can use this mass library. So we are not going to use this any of this following things. Okay, there are some they have also given the code, so we are going to use this code. We are just create our own simple functions. Okay, so let's work on this particular function in RStudio. Okay, let's see how it works in RStudio. Okay, let's look at the RStudio code. Suppose I'm just considering this, let's say the lambda will be the 5 here. Okay, assuming that lambda is 5. So according to lambda is 5, you know, if lambda is 5, then very easy to one can integrate that function. So if you're saying lambda is 5, let's generate the lambda is 5 here. So lambda is 5, and we are generating the, let's say 1000 observations we're generating from the sample size is 1000, and now you're generating x, f of x is generating from the exponential. Okay, so the exponential with parameter 1. Okay, exponential with parameter 1. So how one can use directly which function it is? R exponential. One can generate R exponential to generate the 10,000 observations from exponential. So you can use R. I can just do it here. So R exponential. Okay, so we have generated the 1000 observations, 10,000 observations from the exponential. And now what I'm doing here, I am just based on this observation, generated observations, I am obtaining x power 2 lambda minus 1. Right? You have remember this h of x function. So this is your h of x function, h function. Okay, h of x function. And this is your f of x function. So we are generating from the PDF, and based on generated PDF, we are computing that h of x. Okay, and now we are obtaining the mean of that h of x according to the central limit here. So if you just equate this as a mean of your h of x, just look at what will be the value of this. So this is the mean will be this. We are not so far interested in variance part. Now this is the mean of your h of x function. So definitely this answer and this answer has to match. I think it should match. Let's see. Okay, so this gamma function is coming 24. Okay, 24. So we have, I think, not generated this h of x here. We'll generate h of x here first, and then find out. Look at this expression. Look at this expression. Now it is coming to 24. So if you just observe here, we have the so much difference in between using this approximation as a Monte Carlo technique and normal, because it is your deterministic value, right? This is your because gamma because it lambda is 5, so it is 4. So gamma 4 you can calculate, it just turns out to be 24. This is your mathematical model which will give you the exact value. But whereas the simulation which you have used, that is basically That is basically a simulating the observation. So it is going to be differ from your deterministic value. Okay, so if you just generate again, look at these values: 23, 24. Again generate 21, 24, 23, 25, 21. So what you can observe, here, these this particular things will be approximately, you are assuming that because you are saying it is approximated to function. So if you just generate suppose 1 lakh or 10 lakh, and now if you just observe that, you may get the answer approximately same, which is not exactly same. Okay, you may get answers approximately same. So, but you may get almost same. Look at the expression. Can you observe? So as you are increasing the observations, because they are considering the so many zeros, okay, it is take little time because you are generating more than 10 zeros. Now look at the answers. It will take little more time because I think 2, 4, 6, 8 zeros are there. 8 zeros are there. Okay, the answer. So as my number of zeros has increased, you may observe that these values are very, very, very close to the values. Whereas initial cases, when we have just considering 405060, it's like there are much fluctuation in my you may say my estimated value. This is my exact value. Okay, so these differences will give you the bias of that particular estimate. Okay, so this is just a simple example when your function h of x is a complicated. So you can take the help of your f of x function. So you can generate the observation from f of x, and then you can take the mean of that h of x function, will give you the ultimate answer for that particular integral. Is that clear to all? Basic concepts of the Monte Carlo technique? Yes. Any
Yes.
query? Any query, anyone? Those who are present here? Please let me know. We'll do little simpler example. Don't go to the much detail of this. Whatever basic is required for MCMC, we can just check, and those concepts we will clear via the theory. Okay. Look at this one. So next is a classical Monte Carlo integration, which is required, again basic here. Okay. So let's understand that first, and then we'll have one problem based on this. So before applying our simulation, you must have a little concepts of your functions and all. So as I have given, this particular integration functions can be written in terms of expected value of my h of x under the function f. So first you're simulating the observation from the f, and then you are obtaining the expected value of h of x, which is same as when you just consider approximating distribution. So it will be equating with your h bar, means it's a mean of this function, which is same as 1 upon n summation j running from 1 to n h of x. Okay, so that is the basically mean that just we have discussed. And almost you can say that, surely you can say that when sample size will be increases, your this particular functions will be always equal to the expected value of h of x, using the concept of strong law of large number and all. Okay, similarly one can compute the variance, which is the variance of h bar x, which is h bar n 1 upon n h of x minus, that is the mean you have already obtained, square f of x d of x. Okay, which can be written as usual definition, usual estimates of your variance 1 upon n square summation h of x I minus h bar ka whole square. Okay, so these two concepts you must go through and understand properly. Okay, so if you want, you can just I can just highlight these things because these are going to be little you can understand. Okay, so using this function one can have the mean. Similarly, so this is these two things are required. Then further we have this particular expressions. So here I'm not writing anything, so that I will just recording here. So I will just put it on YouTube. You can watch. Yeah. This function is required. So estimated value we can estimate using this particular function. So this is your estimated value. Okay. And by CLT, one can say that the shape becomes the normal. Okay. A shape becomes normal shape. Okay. So this will be just go through that. That concept is very easy. So that we will not much discuss about that and all. Let's go to ahead. Let's try to do this example. Let's see how one can able to solve this particular problem. Okay. So this is my function h of x. I want to integrate this function with the range 0 to 1. So I have to integrate this h of x 0 to 1 f of x d of x. Okay, which is maybe integral 0 to 1. So my function, so here my PDF is uniform. Okay, and I want to just find out the integration of this 0 to 1 this function into PDF f of x d of x. Okay, and so usually you can here you can create. So this function is complicated function. H of x is a complicated function, so you cannot generate the observations from here. So we have to take the help of f of x. So we generate the observation from f of x first, and once you generated the observation from f of x, we can define the function, and you can obtain the at generated point you can obtain the mean of this h of x. Okay, so first we have to generate from uniform. How it works? You can generate from uniform first. So you can use R uniform, and then this is your x, and at this point you may compute again h of x, and then again you can find out the mean of this h of x. Okay, so this will give you this particular integration ka value. So we are interested to obtain here what? Integration 0 to 1 this h of x function f of x d of x. So that's why here the Monte Carlo integration is required. Okay, so let's see how it works in RStudio also. But just look at this expression represented upper panel of figure 3.3 and evaluating this. Okay, just look at this figure number 3.3 here. So you may just observe at different values of my this generated, and here we have a sample. So how much fluctuation is there in my data set? Okay, so there are a lot of fluctuation from here to here. So each time when you generate the observations, it will fluctuate a lot. Okay, but let's see how it works in RStudio. Let's look at these values in RStudio. So the code which is written in the book, they have given slightly in the complicated way. You have to just take the important from that particular code. Okay, just look at how we can write your own functions and all. Okay, so suppose we have the function h of x. So my function is like cos 50x plus sine 20 over 2 okay square. So now we suppose we generate the 10,000 observation. Just say c dot sig will be 2 by default, so that we get each time we get the same observation. Now we are generating first 10,000 observations from uniform 0, 1. Right? So let's generate this first. Dot sig, and now I'm creating the function h of x. So h of x कैसे create करेंगे हम लोग? It is cos 50 plus sine 20. So one can either take term 1, term 2, term 1, term 2, or instead of y you can take x also, because that is also fine, because x is already defined here, so we cannot take x, so we can take y. So term 1 will be the cos 50, so sorry, sin 50, so sin 50 into y. Term 2 is a sin 20 into y. And now term 1, term 2, whole cap 2 is square. So this term 3 becomes term 1 plus term 2 cap 2 square, and then you have to return to this particular term 2. One can write directly also. It is a function of like cos 50 times y plus sine 20 times y whole cap square. Okay. So this is only used when you have the very big complication, like big functions here. So one can use single term and you can try to get that. Okay. So you can define h here. So this is my h function which is working. Now at this h we have generated x observations, so you can calculate here, mean of this, right? H of x, h of x क्या है मेरा? H of x is a function. So at this function, whatever value of x you have generated, you will find out. So let's find out this function. Now look at these values. Suppose just plot these x values and h of x value. Look at this value, how it works. Look at this. It's exactly same which was matching. So a lot of fluctuation is there in my system. Can you observe? So a lot of fluctuation is there in my system. Okay. And look at just finding the mean of this function. Means mean of my h of x, which is actual answers of that integration. Okay. So ideally it should be 0.96, but this is a simulated mean. Okay. This is your simulated mean using this sample. Now just look at the actual value of this. So this is the actual value, which is 0.9652, and this is your simulated value. So there is not much fluctuation, means after third digit it is changing. So as you increase the size here, suppose you're generating 1 lakh observations, and now if you just run this portion, and now you can just observe, so this is going to be same, this value is going to be same. Okay. So this was your actual mean, and now look at this integration. Now you know observe. We are very close to your estimated value. We are very close to your true value. Are you getting this concept how it is implemented? Yes, students. Can you observe? Yes, can you understand?
Yes, sir.
So any query here in this question?
Sir, mean value of h of x and the mean value of
The mean value of h of x is same as your integration value.
okay, sir.
Okay. Suppose you want to generate the, you want to just create a loop and storing your value, that is your estimated value, to store in particular, you may say in estimate, and now then you're computing the mean. So how one can do that way? So suppose you're generating 10,000 observations, okay, from 500 observations, let's say 10,000 to 1,000 to 10,000. Okay, so look at this. So here we have around 19 observations. So length you can observe, which is 19. Now I'm creating here one empty vector where I'm going to store these estimated values each time. Okay. Now just create a loop here. So these functions, these functions, I have kept it same. So may the h functions remain as it is. And now I'm generating my x observations from uniform having n of k. Okay. N of k means it will take the first value, then it will take the second value, it will take the third value. So first time I'm generating 10,000 observation, next time 1500, next time 2000, and so on till n1, means till 10,000. Okay, and each value I am storing in my k, which is my mean of my h of x, which is my mean of my h of x. And then I will just draw the plot of this, and I will integrate that function, which is going to be same again, and I'll put the line, and then let's see how much fluctuation is observed in my data set. Okay, so let's try to run this, and let me know if you have any query in this problem also. Let's look at the plot here. So these are my estimated values. Okay, so first time mean is coming this, second time mean is coming this, and so on, right? But this is my actual mean. Let's draw the line. So look at here. So my mean is actually here, approximate. This is my actual answer. This is my actual answer. So we have drawn here 1 to n1, which was around this 19, 1 to 19, this part. Okay. So length will be the 19. And according to that, he's estimated these values and they have plotted the data. So we can observe the fluctuations यहाँ पे अपने को observe. So this is the one way. This is another way of using the loop. One can able to generate the observations. So here we have actually 19 observations. We are generating the 19 observations. In each time we are estimating the value. So we can take the first estimate, you can take the second estimate, you can take the third, up till 19 estimates. So I have obtained 90 estimates, and 19 estimates करने के बाद the mean of that h of x will be that is a final value estimate, which is fluctuating here. You can observe, okay, which may be maybe based on the sample, it is fluctuating. Any question here? Anyone? Just go through this code, how it works, or if you want to cross check with me, you can done with me, no problem.